Okay, so what I want to do now is develop the equation of the tangent plane. Okay, so the tangent plane, remember that we said that if the partials exist, then we have this plus sitting up on the graph, right? The two tangent lines in the x direction and in the y direction at every point. And the two lines prescribe a plane. Okay, I want to find the equation of that plane. Okay, and remember that just the existence of the partials doesn't guarantee that that plane is in fact the tangent plane, but that's going to be the candidate to being the tangent plane. If everything is nice and smooth, it is going to be the tangent plane. Okay, let's find its equation. And this is really a geometric discussion. It's going to take us back to vectors and normals and stuff like that. And so let's do it. So first of all, a reminder from single variable calculus, the equation of the tangent line of f of x, function of a single variable, at a point x0 is y equals f prime at x0 times x minus x0 plus f at x0. You all know this, right? This is the equation of the tangent line to a single variable function, right? Everybody? Okay. So what I want to do now is, let's look again at this drawing, which is still on the board. I want to find the equations of these two lines. Okay, this line was the tangent to this graph, which was the graph of the function when we froze x0. We looked at the two-dimensional f, but froze x0 and regarded it as a function of y alone, where x0 was a parameter. That's this blue line here, and this was its slope. This was its tangent line. Okay? So let's call this one, this picture is getting pretty detailed, but we're still going to use it. So let's call this line here, this tangent line, let's call it number 1. And let's call this line here, let's call it number 2. Okay? And we want to find the equations of the first line and the second line. And when we have two equations of lines, we can find the plane that they generate. Do you agree? Okay, that's what I want to do. So what is the equation of line 1? Line 1, so every point on line 1 has x, y, and z coordinates, right? The special thing about line 1 is that all the points along this line sit above this line. They all have a fixed x value of x0. Do you agree? So line 1, let's erase this and write it here. Line 1, this line, the x's are fixed. They're all x0. It's a cross-section of the entire picture, only along x0. Do you agree? Okay. And it therefore lies in the variables are y and z. Okay, there are y's and z's playing roles. Okay, and it's given by, I'm going to use, I have to take a look back at the previous board. I'm going to use this. Okay, but the role of x is now going to be z. Okay, sorry. Y is going to be played by z. That's the value. Okay, and it's going to be given by f prime, well, it's df to dy at the point y0 times y minus y0 plus f itself of y0, all with fixed x0s in between, and this is going to be z. Tell me if you agree. I'm going to write it. So z equals along this line, the z value relates to the y value precisely as the equation of a tangent line to this curve. So z equals df to dy, df to dy at x0, y0, times, I don't have space here. Let's do another thing to make, okay, fine. Z equals df to dy at the point times y minus y0 plus z0, where z0 is this thing. Let's call this z0. F at x0, y0. We're going to call that z0. Okay? Do you agree? It's the equation of a line through this point, x0, y0, z0. Okay? But x0 is fixed. I'm only thinking of y and z. So it's an equation of a line going through y0, z0. Everything is in the yz plane, going through y0, z0, with slope f prime y, the derivative of f with respect to y. Can you picture that? Okay, you may need to think a bit. Okay, think we're slicing like this. There's only y's and z's, and it's z as a function of y. Okay, good, everybody? Raise your hand if you're with me. Okay, so some people are raising their hand, other people, few are not, and some people are doing this. That's interesting. Okay, let me try to say that again. The first thing you have to grasp, if you want to understand things, the most important thing to grasp is that I'm looking at a cross-section of the picture. And what I'm seeing is a totally single variable picture. Okay, maybe let me draw that single variable picture for you. I'm only looking at the cross-section. Down here, there's this variable axis, but it's not the x-axis, it's the y-axis. Do you agree? Y is varying here on this red line. Do you see that? Up here, this is still the z-axis, and above this varying y, at a fixed x0, this is the graph. I have this graph here in blue. That's this. And I'm looking at a specific point. That's this point y0. Okay, and I want it to have a slope at that point. Okay, and I'm looking at this point y0. And I'm trying to find the equation of the tangent line, this thing. Okay? And whenever this is f. Is this clear? Do you understand what I just drew here? This is this, and this is line 2. Oh, line 1, sorry, line 1. Clear? Is that clear? Okay. So what is the slope of this line? What is the equation of this line? Precisely like we wrote there. Y equals f prime of x0 times x minus x0 plus f at x0. But y is now z, x is now y, and f has all these x0s in them that are fixed. That's what I wrote here. So y, z, equals f prime at the point, the derivative with respect to y, because y is the variable, times y minus y0, plus the value at the point, f at y0, which is z0. Clear? Now raise your hand if you're with me. Okay, very good. Okay, so I'm going to erase this. This takes some thinking, okay? You have to think about the picture, figure it out for your own. Don't be afraid to get your hands dirty. Take a piece of paper and start drawing on it. Try doing it by yourself. Try moving it. Try picturing it. You have to play with it until you get the idea. This is maybe the most important idea in this entire course. If you understand this, you're going to understand a lot of stuff that's coming on next. Okay? And if you're missing this, you're missing something so basic that you're going to get so confused later on. Okay? So please make sure you understand this. And if you don't, you can, of course, come and ask. Okay? Please do that. Okay, so So this is line 1. I want to rewrite it. Let's call this thing, just to make life simpler, let's call this thing b. Okay, the derivative of f with respect to y at the point, we're going to call it b. The temporary name. So what I got is a line. I can rewrite this thing as z minus z0 equals b times y minus y0, or z minus z0 divided by b equals y minus y0 divided by 1. Okay, do you see an equation of a line? Okay, x is x0. Let's rewrite that as well. Do you see that this is an equation of a line in what we called canonical form, not in parametric form? Do you see that? Okay, good. What's the direction vector of this line?
No, 0, 1, b.
Right. The direction vector, which we denoted by a for this line, is 0, 1, b. 0 because this thing indicates that there was a 0 there. That's why x equals x0. Okay, everybody remember what I'm talking about? Okay, so that's the direction vector of that line. Similarly, I could do the exact same analysis for this second line. Okay, and I'm going to write it, but I'm going to do it a bit more quickly. I'm not going to go through the entire discussion again because it's completely analogous. So let me just write it. So line 2 is given by, this time y is fixed, y is y0, and the z is given by df to dx at the point x0, y0 times x minus x0 plus z0. Again, let's denote this by a. So what we get is y equals y0 and z minus z0 divided by a equals x minus x0. That's the equation of line 2. Okay? And what's its direction vector? Let's call it a2. The direction vector is 1 for the x's, because it's divided by 1, 0 for the y's, and a. Does everybody agree? Okay. So now we have two lines. We have their direction vectors, and we want to find the plane that these two lines prescribe. How do we find the plane?
Cross the direction.
Right. We take a cross product of these direction vectors. That would give us something perpendicular to both, right? That would be the normal to the plane. Do you agree? And then we have to find the plane with that normal that goes through the point x0, y0, z0. Do you agree? Let's do that. So a normal to the plane generated by lines 1, 1, and 2 would be what? So let's call it n. So n would be I, j, k times, what was it? 0, 1, b was the direction vector of line 1, and 1, 0, a is the direction vector of line 2. Do you agree? Right? It's the vector product of the two direction vectors. Okay, so what we get is in the I direction, we get a. In the j direction, we get minus b, but with the minus from the j, we get b. And in the k direction, we get minus 1. This is the normal. And remember that a was the partial with respect to x, and b was the partial with respect to y. Good? So now what's the plane? The plane itself. So the plane the candidate for the tangent plane, and it's a candidate because we just know that it's spanned by these two lines. We don't know yet that it's actually a tangent plane. Okay, that's the discussion from the previous discussion. So the candidate for the plane is going to be a plane with normal AB minus 1 that goes through the points x0, y0, z0, which was f of x0, y0. Okay, so let me write it. So it's a x minus x0 plus b y minus y0 minus 1 z minus z0 equals 0. That's the equation of the plane. Do you agree? Now I just want to rewrite everything and throw back in stuff we had notation for. So this was f of x0, y0. That's what z0 was. This was the partial with respect to x. And this was the partial with respect to y. So I'm going to rewrite it as z equals minus minus z0, so plus z0, so f of x0, y0, plus df to dx at the point times x minus x0 plus df to dy at the point times y minus y0. That's the equation of the tangent plane when it exists. And just existence of the partials, so you can automatically see that if the partials don't exist, obviously the tangent plane is not going to be defined. Okay, so this is a necessary condition, the existence of these partials. Okay, but it's not sufficient. There's going to be more to require in order to guarantee that this plane, the plane is defined, but in order to guarantee that it's in fact a tangent plane, we're gonna need to somehow say more, and that's the notion of differentiability. We'll get to that. Questions about this? Is it clear? Is it clear how we got it? Everybody? Okay, so coming up next is really a discussion of this notion of differentiability, and it's going to stem for somehow looking somewhat differently at the definition of the derivative for calculus 1. Okay, we're going to generalize a slight modification, a different way to look at the same thing of the derivative, which you know from Calc 1. That's next.